The universe is censoring you, and here's why. He lowers the last shutter and kills the lights. On the screen, two bright bands blaze to life, then, as if embarrassed, dissolve into a thin spray of dots. He flips a switch, the dots sharpen into razor stripes. Another switch, the stripes vanish again. He laughs once, quiet and uneasy. The machine isn't broken. The universe is refusing to commit. This lab trick will haunt everything that follows, because what looks like a party trick is actually a code, an access policy on reality. To see how the universe hides its tracks, we have to go back to the first glitch, the vanishing path. The first glitch, double-slit and the vanishing path. They thought they were just firing bullets of light. Two slits, a screen and a beam. Open both slits and you expect two bright patches. Instead, the screen blooms with alternating bright and dark fringes interference, as if each photon were a wave interfering with itself. Fine, call it a wave. But then turn the beam down until photons arrive one at a time. The fringes still build up over hours. A single event spread across possibilities somehow knows both paths. Get this, if you ask which slit it went through, the pattern changes. Put detectors at the slits to track the path and the stripes vanish. You recover two fat blobs. Particles march through one slit or the other. The moment the path is recorded, the interference dies. Take the detectors away and the interference reappears. It's the first time physics whispers. It's not just what happens, it's what can be known. Here's the thing that gnaws at people. It isn't the act of seeing with your eyes that matters, it's the information being available in principle. A faint scatter off a dust mote, a whisper of a field, anything that leaves a recoverable trail counts as which path information. The universe seems to run an audit. If path information exists, the interference is off limits. If no such record can exist, interference is allowed. It reads like a permission system. Now remember, this isn't metaphysical hand-waving. It's been pushed hard. Physicists built delayed choice experiments, where the decision to preserve or erase which path information is made after the photon has already hit the slits. The results hold. When the setup would allow the path to be known, interference doesn't appear. When the setup ensures the path can't be known, even if that lock is applied later in the apparatus, interference emerges in the tallied coincidences. They didn't find time travel. They found that what counts is the logical availability of information in the total arrangement. But here's where it gets crazy. You can tag the photon with a subtle marker, say, a polarization twist tied to each slit, so that in principle the path is encoded. Interference disappears. Then you route the photon through a device that erases the correlation, scrambling the tag so the path becomes unrecoverable. Suddenly, in the right subset of detections, the interference returns. You didn't undo the past, you removed the record. The universe acted like a strict librarian. If a path record exists, no interference. If the record can't exist, you get the fringes. Pause on the human moment. A young grad student stares at a black screen waiting for dots to accumulate. The lab smells like warm electronics and old coffee. Her advisor told her this would feel wrong. She watches 1,000 tiny pinpricks bloom into a ghostly zebra. It feels like the machine is choosing when to tell the truth. Meanwhile, something else is happening in her head. If information is the gatekeeper, then the limit isn't just energy or distance. It's access. The universe might not be hiding things behind brute force walls. It might be hiding them behind conditions. You can't see the wave and the path at the same time because those are different questions. Ask one, and you lock the other behind a door you just closed. This was the moment everything changed for how some physicists talk about reality. The double-slit becomes a parable about limits. Not you don't have the technology, but you aren't allowed that combination of facts. It's a censorship code that doesn't need an enforcer. The rules live in the math. Complementary observables, uncertainty relations, the no cloning of unknown quantum states. They all rhyme with the same idea. Information can't be copied freely, tracked everywhere, and still behave like a wave. Unknown to most viewers, there's another twist. It isn't measurement in the Hollywood sense that collapses anything. It's decoherence, uncontrolled entanglement with an environment. A photon brushes past a stray molecule and leaves a whisper of which path. That whisper propagates into a room full of air, then a building, then the world. The path becomes, in practice, knowable. Interference vanishes. Remove the environment, shield, cool, isolate, and the interference returns. It's not magic, it's bookkeeping. 3 days earlier, the same grad student had tried to peek, gently turning the detectors down to barely register. The fringes blurred but didn't disappear entirely. That's the other rule: partial knowledge, partial interference. The contrast of the stripes maps to how much path information leaks. The less you could, even in principle, recover, the sharper the wave-like pattern. It's as if the universe charges an interest rate on certainty. What nobody knew at the time, standing by that screen, was how far this logic would travel. To black holes, where information seems to fall and vanish, only to whisper back in radiation years later. To gravitational wave observatories pushing against quantum noise, forced to reshape the vacuum to listen harder. To pulsars across the galaxy, whose ticks carry spacetime's murmurs only when correlated just right. The same question keeps surfacing: what can be known, by whom, and when? But hold that thought. For now, keep your eyes on those vanishing stripes. This is the first glitch in our story. A tiny, stubborn experiment that teaches a harsh lesson. Reality isn't a menu you can order from freely. Every question you ask locks another door. And once a record exists, even a fragile one, the universe treats the answer as final. The speed limit and the toll. Light, causality, and channel capacity. The grad student walks home under streetlights that hum like old radios. She keeps replaying the vanishing stripes, but another constraint presses in. Nothing outruns light. Not a rumor, not a push, not a clever hack. That speed limit isn't a traffic rule. It's the scaffolding that keeps cause before effect. Try to send a signal faster and you scramble the order of events for someone else's clock. Causality tears. The universe says no. Get this, if information has to live inside light cones, then every message you send is fenced by geometry. The future you can influence is a cone widening at light speed. Everything outside stays mute until time brings it inside. It's a map of who can know what and when. That map is the first half of the censorship code. You can't reach beyond the cone without rewriting time. But there's a second half, and it hits when you try to talk through the cone. Even if light speed is generous, the channel itself takes a toll. Noise lives everywhere, in the thermal wiggle of electrons and the quantum jitter of fields. Claude Shannon, working in a wartime lab, framed it like a wager. You can send symbols down a noisy wire, but the wire will flip some. The question isn't, can I send forever? It's, at what rate can I send reliably? He gave the answer a name: capacity. Here's the thing. The microscope in her lab and the fiber in your phone are both channels. Each has a maximum rate measured against its noise. Pile on more power and you don't get infinite clarity. You get smearing, heating, crosstalk. There's an optimal code, a sweet spot, but there's always a ceiling. That ceiling is brutal because it isn't taste or budget. It's mathematics. Past capacity, errors drown meaning, and no decoder can resurrect what never made it through. She hears this again in a different key the first time she tour a radio observatory. The guide points at a dish listening for whispers from a pulsar 10,000 light-years away. We integrate for hours, he says, because noise doesn't stop. You have to average it down. The universe isn't quiet. To know more, you wait longer or bring more area. Either way, you pay. Meanwhile, something else is happening a continent away. In shafts of vacuum, LIGO's lasers bounce between mirrors, straining to hear spacetime stretch by a fraction of a proton's width. They hit another toll booth: quantum noise. Shot noise from the grain of light. Radiation pressure noise from the light punching the mirrors. Squeeze the light, reshape the vacuum's fluctuations, and you can trade one noise for another, move the wall a little. But there's a wall. They didn't hit shoddy engineering. They hit the standard quantum limit, born from the same bookkeeping that killed those stripes. Now remember, capacity isn't just about the watts you pour in. It's about bandwidth, the range of frequencies you can occupy, and about the temperature of your environment. Landor's principle sneaks in here. Every bit you erase dumps heat somewhere, at least kT-ln2 of it. That heat becomes noise. The effort to make a clean record dirties the room. Try to build a daemon that separates fast molecules from slow, and you discover the cost hiding in its memory. The toll is universal. Moving, storing, erasing information leaves a thermal wake. She pulls at that thread and finds a limit on speed that isn't about rockets. The Margulis, Levitin bound, the quantum side of the ledger, says there's a minimum time to evolve from one distinguishable state to an orthogonal one, set by your average energy. There's a fastest clock hidden in physics, and even a perfect processor ticks no faster than that. Computation is a kind of motion through configuration space, and it has a speed limit too. While all this plays out, astrophysicists stitch together a different kind of detector, a pulsar timing array using millisecond pulsars as clocks scattered across the sky. Each tick travels at light speed, soaked in noise from interstellar plasma and clock drift, but correlate many pulsars over years, and a pattern leaks out. A quadrupolar correlation, the Helling's, Down's curve, a fingerprint of a gravitational wave background. The trick isn't brute force hearing, it's coding the galaxy as a receiver and paying with time. Capacity again. Widen your effective bandwidth by adding sources, lower your noise by averaging. The toll is patience and calibration. This was the moment everything changed for her sense of hidden. It wasn't that secrets were tucked behind walls you could blow open with more energy. They were throttled by the joint laws of causality and capacity. You can't shout past a light cone, and you can't whisper below the noise floor faster than Shannon allows. And when you try to clean the message, you heat the room. Here's where it gets personal. She tries to build a better measurement in the lab, cooler detectors, darker rooms, smarter codes. Each success feels like prying open a shutter, but every 30 seconds a new constraint shows up. The power supply hum sneaks into the data. The refrigerator dumps heat that ripples into the optics. The squeezed light lowers one hiss but raises another. Progress is real. The toll booths are too. So the code sharpens. Spacetime sets where information can go. Noise and thermodynamics set how much of it survives. Quantum rules set how cleanly you can extract it. The universe doesn't just hide by distance. It hides by rationing your access, charging you in time, energy, and entropy for every extra bit you demand. Planck units, pixels, frames, or just convenient. She keeps a sticky note over her bench. 1035 meters, 1043 seconds. Planck length, Planck time. They read like the fine print at the bottom of the universe. People talk about them like pixels and frames, as if space were a screen and time a refresh rate. It's tempting. You want the world to snap to a grid so you can count it. But here's the thing. Those numbers aren't carved into bedrock as a hard lattice. They're built by mixing three constants: the speed of light, Planck's constant, and Newton's G. Put them together, and you get the scales where quantum and gravity stop ignoring each other. That's why those units haunt theorists. Not because we've seen the pixels, but because this is where two different rulebooks both insist on being heard. Meanwhile, something else is happening in the literature. People argue about whether the Planck length is a real cutoff, a smallest possible tick of space, or just a convenient yardstick we made from our favorite constants. The lab isn't going to settle that this week. LIGO doesn't see a grid. Pulsar timing arrays don't either. Instead, she hears the question reframed. Even if the world isn't literally pixelated, could there be a limit to how finely information can be packed into a region? Now remember the Blackboard lessons about entropy. John Bekenstein took gravity seriously and found a bound. The maximum information inside a sphere doesn't scale with volume. It tracks the area of its boundary. That sounds like her sticky note, but sideways. Less space has pixels, more. The bookkeeper only lets you write so many bits on the surface before anything inside collapses under its own accounting. The holographic hint lands. If there's a censorship code, maybe it's a boundary rule, not a grid rule. Get this? If you try to cram more detail into a region than the bound allows, you don't get sharper pictures. You get a black hole. The universe enforces the limit by making your hard drive gravitationally self-destruct. It's a nasty kind of compression. Exceed capacity and your data becomes an event horizon. Whatever Planck really is, she can feel the teeth of a deeper principle. The fine print shows up as area. She tries to translate this into lab instincts. If there's no direct microscope for 1035 meters, what would a Planck scale limit look like downstream? Maybe as a floor-to-measurement noise you can't squeeze past. Maybe as a ceiling on how fast a system can compute reliably without turning into heat. Margins where attempts to sharpen reality bounce off thermodynamics and gravity together. Planck doesn't need to be a pixel. It can be a toll booth where two departments, quantum and geometry, share one cashier. Here, S where she hears from older colleagues who chased quantum foam, those old pictures of spacetime bubbling at tiny scales. Cute metaphor, shaky prediction. No resonant hum of foam in interferometers, no easy signatures in cosmic light. But the absence of a pixel click isn't silence. It's the same pattern as before. The universe hides by redirecting the question. You don't get to zoom in. You get to count how many distinct messages can live in a patch before gravity edits them. 3 days earlier, she'd been reading a paper tying computation to energy and time. Minimum steps per joule, minimum time per step. It rhymed with the sticky note. Combine those with the Bekenstein bound and you get something like a cosmic budget sheet. A maximum number of operations a region can perform before its own heat and gravity push back. Planck lurks in the constants, but the visible rule is about how many clean distinctions, bits, you can make before the ledger flips red. Meanwhile, out on the horizon of theory, black hole physics hits the same chord. The entropy of a black hole scales with area in Planck units. Hawking radiation leaks information in a slow, coded drizzle. The page curve says the ledger balances in the long run. Whether or not space is pixelated, the accounting is, and the unit on the invoice is built from those same constants. Planck shows up as the size of a bit written on the boundary. She thinks back to the double-slit. There the code said, you can't have full wave and full which path at once. Here, the code says, you can't store unlimited distinctions inside a region without paying in curvature. Both are access rules. Both are about which questions the universe lets you ask together. Planck, then, isn't a brick. It's a watermark that appears when you try to combine questions from both rulebooks. Now remember the human moment. She peels the sticky note off and writes in smaller letters. Not pixels, policy. It keeps her honest. Because if you chase Planck like a grid, you start seeing ghosts in your instruments. If you treat it like a policy, you design better questions. You ask about capacities. How many qubits survive decoherence in this volume, at this temperature, with this gravity? You ask what must happen when your code exceeds the boundary's allowance. This is the moment everything shifts. Planck units move from myth to mechanism. They don't tell her that space is chunky. They tell her where the universe's two auditors meet to reconcile the books and what currency they use to do it. She doesn't need to see the pixels to feel the limit. It shows up as the rate you can compute, the bits you can store, the heat you must dump, and the area that quietly tallies it all. Landor's bill, the heat of erasing and the cost of knowing. She thought the hard part was getting the data. Turns out the receipt comes later. In the quiet after an experiment, when the files are saved and the sensors spin down, something subtle but absolute kicks in. Landor's rule. Erase a single bit, truly erase it, and you owe the universe at least kT ln2 of heat. Not a suggestion, a floor. The cost of clearing a memory cell, of resetting a register, of saying start fresh without ambiguity. Every act of forgetting leaves warmth somewhere. Here's the thing, this isn't about clunky hardware. It's about logic. You can compute reversibly and dodge the toll for a while, but the moment you compress outcomes, discard branches, or overwrite a register without keeping a perfect history, you've paid. The demon in Maxwell's thought experiment learned this the hard way. It could sort fast molecules from slow and lower the gas's entropy, but to keep working, it had to clean its notebook. The heat that spilled in that cleanup repaid the debt. Entropy never lost. The bookkeeping just moved columns. Meanwhile, in the lab, she feels the bill arriving in mundane ways. A firmware update that writes logs to the same disk again and again. The data pipeline that prunes raw streams into tidy summaries. Each reset warms a component, nudges a bath temperature, adds a flicker to the noise the next run must average down. The act of knowing, of making a record that favors one set of bits and discards the rest, creates heat. The act of preparing to know again by erasing creates more. Now remember the earlier rules. A measurement is a controlled entanglement with a pointer that you can read. That pointer needs a standard state before the next shot. Reset it and Landor taps you on the shoulder. You wanted clean, fresh, ready states, pay in heat. Try to hide the heat in a refrigerator and the fridge dumps it to the room. The room breathes it into the building. Follow it far enough and your measurement spills entropy into the world. The cost of certainty ripples outward. Get this, there's a strategy to dodge the worst of it. Bennett showed you can compute in a way that's logically reversible, uncomputing ancillas and carrying your garbage bits forward like a tidy traveler. But the universe is merciless about one detail. To deliver an answer to someone else, to compress your past into a small payload, you must eventually throw away branches. If you never erase, you're just moving the mess. To communicate a conclusion, to turn sprawling microstates into a crisp yes or no, you erase. The eraser's warmth is the price of clarity. She hears this toll in the analytics of her own microscope. The detector's firmware takes a continuous stream and bins it into counts. Binning is erasure. The compression algorithm that saves space on the server is erasure. The thresholding that decides event or no event is erasure. Each is a little furnace that must be paid for in cooling power and noise budgets. Every choice to know more cleanly here means knowing a bit less cleanly there because the heat goes somewhere. Meanwhile, information theorists phrase it in the cleanest way possible. Entropy is missing information. When you erase, you increase missing information about the erased degrees of freedom. That missing information doesn't vanish. It shows up as heat in the environment's microstates. It's the same ledger from the double-slit, but now the column headings are bits kept, bits tossed, and heat emitted. The code is consistent. Trackable distinctions demand energy. Discarded distinctions demand entropy. 3 days earlier, she tried a trick she'd read about. Use reversible logic to post-select on rare events without erasing intermediate junk. It worked, until she had to report the outcome. The moment she shared a 2-bit answer from a 1,000,000-bit scaffolding, the scaffolding had to be cleaned or forever maintained.